for the grade 12 chemistry class of St. Peter's College, Colombo for Nikapu branch. In this lesson, we are going to discuss about the P block group 17 elements. First, let's see what are that elements. They are fluorine, chlorine, bromine, iodine and astenine. In this lesson, we are going to consider about these elements. First, let's take the group trends. All these elements normally we call halogens, and these halogens are very reactive, and we cannot find them as elements. Normally we can find them as compounds because they are very reactive elements. Among these elements, fluorine is the most electron negative element, and it shows oxidation state of -1 and 0. But other halogens show oxidation states from -1 to +7. But the compound of borine that have +7 oxidation state are very unstable. And there are some group trends. Due to a smaller atomic radius of fluorine, it shows different characteristics than the other elements. You know, as usual, first element of all the groups shows different characters than the other elements. So the same thing is happening here for group 17. Fluorine is the first element and it shows different characters than the other elements because fluorine consists very small atomic radius, and it is the most electron negative element in that group. So it shows different characters than the other elements. And if we take the oxidizing ability of these halogens, we can see the oxidizing ability is decreased when we go from top to bottom of the group. Then reactivity. If we consider about the reactivity of the halogens decrease when we go from top to bottom of the group. This can be explained by using these two reactions. If we consider these two reactions, first one, chlorine react with bromide ion and it forms chloride ion and bromine, because in here chlorine has reduced and bromine has oxidized to Br2. Bromide ion has oxidized to Br2. That means, and if we consider the second reaction, if we react Br2 with iodine or iodide ion, it forms bromide ion and I2. So here you can see when we go from top to bottom of that group, the reactivity of halogens decrease. That's why here bromide ion form bromine and iodide ion from here iodine. Then if we check about the natural occurrence of these elements and the physical states in room temperature, fluorine is a pale yellow gas and chlorine is a pale green gas and bromine is a red brown liquid, and iodine is a violet black solid. So you can see here first two elements are gases, and third one is a liquid, and the iodine is a solid. Now we are going to focus on the bond energy of these elements. If we see the bond energy from chlorine to iodine, we can see bond energy decrease. What is the reason for that? Because when we go from top to bottom, the radius of the atoms decrease, and when the radius is decreased, the bond length also decrease, and the bond energy decrease. When radius increase, bond length also increase, and the bond energy decrease. So the values of these three elements we can compare, and we can see that bond energy has here decreased, because if we take, this is the one atom and this one is the another atom of the same element, and this is the bond length. This is the bond length, and when the radius increase, the bond length also increase, and the bond energy decrease. So you can check that with chlorine, bromine and iodine. But in here, fluorine has deviated than the other elements, because the bond energy of fluorine is less than chlorine. What is the reason for that? Because if we take the fluorine, this is the one atom of fluorine, it consists a non-bonded valence electron. Here you can see there are three pairs of electrons, and the repulsion, the electron repulsion of fluorine is a higher value than the other three elements, because fluorine is the most electron negative atom in that group. So the electron repulsion also a higher value than the other elements. So because of that, the bond energy is a smaller value than the others, because when electrons are repulsing, it is easy to break the bond. So the bond energy is a lower value than the other elements. Now we have to study about the properties of group 17 elements. If we take the ground state electron configurations, all the elements consist S2 P5 electron configuration, and van der Waals radius, you can see here van der Waals radius is increased, because the atomic radius increase and the van der Waals radius also increase. And here ionic radius increase, covalent radius also increase, and you can see melting point here also increase, and boiling point also increase. Electron negativity decrease. When we go down the group, electron negativity decrease. Then if we consider the electron gain enthalpy, we can see here electron gain enthalpy here increase. So you can compare these properties and you can find the pattern of all these properties. So it is easy to remember when you find a pattern. Now in this lesson, there's another part we have to consider about is simple compounds of group 17 elements. Under that part, we are going to study about the mainly 5 compounds. First one, hydrogen halides of group 17. I can give as an example HCl. It is a hydrogen halide of group 17, and HBr, HI, all are hydrogen halides of the group 17. Then we have to consider about the silver halides of the group 17. After that, oxides and oxo acids of chlorine. Then at last, we are going to discuss about the halides of the group 17. First, I take hydrogen halides. These are the hydrogen halides of the group 17. HF, HCl, HBr and HI. Hydrogen halides are acidic in water. We can check that if we dissolve this hydrogen halide in water, it shows acidic properties. If we consider the acidic nature of these halides, if we dissolve hydrogen fluoride in water, it dissociates like this. It forms H3O plus aqueous ion and F minus aqueous ion. And HF has the ability to produce extensive hydrogen bonding. And in room temperature, HF is a gas. So, for the other hydrogen halides, when we dissolve them in water, these halides, we can see here, dissociate totally and gives H3O plus and relevant halide ion. But only HF shows the partial dissociation, because as I told you, HF is fluorine is the most electron negative element. So it not dissociate totally, but other halides dissociate totally. That's why we use this kind of arrow, and it gives these ions. Then HF is a weak acid, but the other hydrogen halides are stronger acids in aqueous medium. As I show you in the previous equations, HF dissociates partially, so it is a weak acid, and other halides dissociate totally, and they are stronger acids. Then this can be explained by using some selected properties of group 17. In this chart, I have shown you that properties. If we consider the melting point, boiling point, bond length and bond dissociation energy, we can show that HF not always show the reaction of not dissociating totally. It is very hard to totally dissociate. But in other hydrogen halides dissociate easily, because if we take bond length, the bond length of HF is a smaller value than the other elements, and bond dissociation energy also a higher value in HF. When bond dissociation energy is a higher value, it is hard to dissociate. When it consists a lower value like HBr, Hi and HCl, it is easily to totally dissociate. And totally dissociate halides, hydrogen halides are stronger acids. So I think you can understand the difference of acidic nature of these hydrogen halides. Then we are moving to silver halides. This is a very important thing, because we use this reaction to identify the different halide ions, chloride, bromide and iodide ion. We can identify easily by using this silver halide reaction. When the silver halide precipitate are formed, they show different colors. Silver chloride is white color, and silver bromide shows pale yellow color, and silver iodide is a yellow color precipitate. And when we dissolve them in ammonia, silver chloride dissolves in diluted aqueous ammonia, but silver bromide dissolves in concentrated aqueous ammonia, and silver iodide dissolves in, not dissolve in both diluted or concentrated aqueous ammonia. So by using these precipitate and dissolve them in ammonium solution, we can identify these ions, whether it is a chloride, bromide or iodide. Now we are going to discuss about the oxides and oxo acids of chlorine. Chlorine form different kinds of oxides. These are the oxides that formed by chlorine, and these are the oxidation states that chlorine shows in that relevant oxide. And if we see carefully, you can see here the formula of the ion of that oxide and structure of that oxo anion. +1 oxidation state shows in hypochlorite ion, and +3 oxidation state shows in chlorite ion, and +5 oxidation state shows in chlorate ion, and +7 oxidation state shows in perchlorate ion. This is a very important thing you have to remember about these ions and what are the oxidation states they show in chlorine in each of these oxo anions. Now we have to consider about the oxo acids. Chlorine forms 4 types of oxo acids, and we have to check the strength of these oxo acids with their structure. Here I have shown you the oxo acids of chlorine and the oxidation states they show in each of these oxo acids. These are the structure. In HClO it shows +1 oxidation state in chlorine and HClO2 +3 oxidation state in chlorine and HClO3 +5 oxidation state in chlorine and HClO4 +7 oxidation state in chlorine. If we consider the oxidizing power of these oxo acids of chlorine change, it is as follows. We can see here oxidation power is decreased here. When the number of oxygen atoms decrease, here only one oxygen atom, here 2, 3 and 4. When the number of oxygen atoms decrease, the oxidizing power we can see here decrease. Number of oxygen atoms decrease and oxidizing power decrease. So these are the oxidation states of these oxo acids, and when we consider about the acidic nature of these oxo acids, we can see here the higher oxidation state shows the stronger acid. That means the variation of acidic strength is like this. HClO shows the lowest acidic strength and HClO4 shows the highest acidic strength. That means when the number of oxygen atoms are increased, the acidic strength also increases. If you see this carefully, you can understand the gradual change of oxidizing power, oxidation state and the acidic strength. How they change with the oxidation state and with the number of oxygen atoms. Then after that we are going to discuss about the halides of the group 17 elements. Most of the covalent halides in group 17 react with water, but CCl4 or carbon tetrachloride does not hydrolyze. There's a reason. Because all other elements in group 17 consist d electrons. As you know, when we go from top to bottom in the group 17, fluorine and chlorine not consist d electrons, but bromine and iodine consist d electrons. So due to non-availability of the d orbitals, carbon tetrachloride cannot hydrolyze or cannot react with water. Then most of the fluorides and some other halides are inert, but the halides of bromine and iodine are react with water. Now we have to see the group 14 and 15 elements, how they react with water. First, I am going to show you how they react with less water. When the group 14 and 15 elements react with less water, if we take the silicon tetrachloride react with less water and form HCl and silicon dioxide. And also phosphorus, it is a group 15 element. It reacts with less water and form these two products. Now how these elements react with excess water. If we would use excess water, the products are different. Here I have shown you that group 14 element, there is a silicon, and silicon tetrachloride react with water and form HCl and H2SiO3. And nitrogen, phosphorus, arsenic, antimony and bismuth, they are group 15 elements. They react with excess water and all form HCl, but the other products are different. So you can check the differences between the reactions of less water and excess water. Now we have to study about the reactions of chlorine. Chlorine is less reactive than fluorine, but chlorine is a strong oxidizing agent. We can check that with these reactions. In these reactions, chlorine acts as a strong oxidizing agent. Here, chlorine reacts with copper chloride, ferrous and ferric chloride. If we check the products, in here you can see how chlorine acts as an oxidizing agent. In here, chlorine has reduced from 0 to -1 and copper has oxidized from 0 to +1 and formed the copperous chloride, that is a white precipitate. And in second one, chlorine has reduced to +1 and copper has oxidized to +2 and formed the copper chloride. It is a light brown precipitate. In third one, chlorine reduced to +1 and here iron has oxidized to +2 and formed the ferrous chloride, that is a off-white precipitate. And here ferric chloride, ferrous oxidized to ferric, here Fe2 plus and here Fe2 +3. It has oxidized and chlorine has reduced and formed the dark green or purple red precipitate. So you can see how chlorine acts as an oxidizing agent. Then chlorine also react with ammonia and act as an oxidizing agent. And with the excess ammonia, it forms nitrogen gas, and with excess chlorine, it forms nitrogen trichloride. In these reactions also, chlorine acts as a strong oxidizing agent. Here you can see chlorine moves from 0 to -1. That means chlorine has reduced, and ammonia, in here nitrogen shows -3 oxidation state, and it moves from -3 to nitrogen -3 to 0. That means ammonia has reduced. Ammonia has oxidized and chlorine has reduced. That means chlorine has acted as an oxidizing agent. With excess chlorine, chlorine moves from 0 to -1 here. That means chlorine has reduced, and nitrogen in ammonia has changed from -3 to +3. That means nitrogen has oxidized, and here chlorine has acted as an oxidizing agent with ammonia. As I told you, chlorine is a oxidizing agent and also a reducing agent. We can check that with this reaction. We have studied this before. You know what is a disproportionation reaction. That means when an element reacting as an oxidizing agent and as a reducing agent at the same time, we call that disproportionation reaction. In here we can see chlorine is acting as an oxidizing agent as well as the reducing agent. If we take this reaction, chlorine react with water and form HOCl and HCl. Chlorine, here you can see chlorine move from 0 to +1. That means it has oxidized, and also it moved from 0 to -1. That means it has reduced. So the both things happening at the same time. That's why we call this is a disproportionation reaction. Then reaction with chlorine with sodium hydroxide. There are two types of reaction. When chlorine reacting with cold hydroxide, it forms different products, and with hot hydroxide, it forms the another products. If we check the first one, if chlorine react with cold dilute sodium hydroxide, it forms NaCl, NaOCl and H2O. But with hot sodium hydroxide, it forms NaCl is same, NaClO3. In here it forms NaOCl. With hot sodium hydroxide, it forms NaClO3. Other two products are same. So you have to remember the difference of these two reactions about these products. Then reactions of oxoanions. I told you that before. Chlorine form the oxoanions, and here we are going to talk about the perchlorate ion. In here, hypochlorite ion is stable at low temperatures and disproportionates at high temperatures. But bromine and iodine are not stable even at lower temperatures. They undergo disproportionation reactions. But the hypochlorite ion is low stable at low temperatures. This is the disproportionation reaction of hypochlorite. In disproportionation, hypochlorite produces the chlorate ion. In here also, chlorine oxidize and reduce in the same time, and so show the disproportionation reaction. Hypochlorite produce the chlorate ion. And if we consider about this reaction, this ion is more stable in acidic conditions. So this disproportionation predominate under the basic conditions. So this is the things about the group 17 elements, and we have to study about another group in P block, that is group 18. I hope to discuss with you about the group 18 in our next video. Thank you for watching this video.